My camera was on vacation as well, so. Okay, great. Okay, so a homomorphism is called an isomorphism if it is bijective. Okay. Now, what is an isomorphism? Basically, two groups, there's an isomorphism between them if they're literally the same. If one is just the other one, but with a mask. Let's give an example. So let phi, well, let's give some properties. Let phi from G to H be an isomorphism. Yeah, an isomorphism. So basically a bijective group homomorphism. What is that? What happens here? Phi, let G be in G, so G is in G. The order of phi of G is equal to the order of G. So an isomorphism will preserve orders. So it maps an element of order 2 to another element of order 2. In particular, the number of elements of order 2 on both sides must be the same. 2. These are some properties. If K is a subgroup of G with K is equal to N, then phi of K, I mean I will not prove these. These are more exercises that you can do, but we'll just use them. Then phi of K is a subgroup of H, where phi of K is N. I mean, you expect that in bijections, right? Because the bijection preserves sizes, right? Yes? No, N is just the size of K. Okay? G is a billion if and only if H is a billion. Three, four. Technically, so everything related to the group are basically the same. G is cyclic if and only if H is cyclic. Let's do one more, let's see. Okay. And phi inverse, we know that since phi is a bijection, I can find an inverse. And phi inverse is also an isomorphism. Okay? So basically, whenever you say an isomorphism, means the two groups are literally the same when it comes to their group structure. Okay? Let's give an example. Now in your assignments, in one of the previous assignments, you have seen the product group, right? So if direct product, let's say. You have seen that if A, let's say, I don't know, circle, and B dot are groups, then A times B is a group. And the operation of A times B, what you do, you take A1, B1 times, I will, anyways. Yes. A2, B2 is A1 circle A1, B1 dot B2. A1 circle A2, sorry. Remember this? You remember this? You proved this, that you have a group, that the Cartesian product of two groups is a group. So that might be a way to generate a group. Now, before we study this group, let's give a nice example actually of two groups that are not isomorphic. Okay. So let's talk about groups with 4 elements. So groups with 4 elements. Now, we will prove later that, well, consider now these 2 groups. Both of these have 4 elements, right? Agree? 4 elements and 4 elements. Are they isomorphic? Could you find a feature in this that is not there? Are they both abelian? They are both abelian. That doesn't work. Are they both cyclic?
Yes.
So this has an element of order 4, right? One has order 4. Agree?
Yeah.
Now, here, what is the largest order you can have? Yeah, see? 2, right? If you add any element twice, you will get 0. Agree or not? Take AB in here, plus AB. What do you get? You get 2A times 2B. So you get 0 mod 2 and 0 mod 2. So every element has ordered at most 2. And here you have an element of order 4. 1, 4 has an element, has order 4. So do you have an element of order 4 in here? Everything is killed, well, anyways, everything is vanished when you add it twice, right? And here you have an element of order 4. So these 2 groups are not isomorphic. Let's give another one. Groups of order 6. How many groups of order 6 we know? We know Z mod 6Z and S3, right? Are they isomorphic? Immediately, yes or no? Are Z mod 6Z and S3 isomorphic?
No.
Can you find a feature in one that is not in the other?
Again, the order?
6 and 6. That works. Yeah.
Isn't S3 not cyclic?
S3 is not cyclic, yeah. It's not abelian, right? S3 and Z6 are not isomorphic. Z mod 6Z and S3 are not isomorphic. So this is abelian and this is not abelian. Okay, now what about Z2 cross Z3? Z2 cross Z3 is a group of order 6, right? Take the elements mod 2. Yes?
So why does the fact that every element has an order of most 2 imply that they're not?
If you look at the first proposition, if G has order n, then phi of G has order n, right? Okay? So they must have the same number of elements of a given order. Okay? Now, Z2 cross Z3, for example, it's a group with 6 elements. Is it isomorphic to any of these? That's a question. Theorem. Let G be a cyclic group with n elements. Then G is isomorphic to Z modulo n Z. Okay, I mean we write this way. G is isomorphic Z. Okay, this means isomorphic. Let's prove that. proof. So consider phi from Z mod NZ to G. I mean, you know, G is cyclic here. Let G equal to G. Let G be generated by G. Okay? So let G be a generator of big G. And send the equivalence class of A modulo N to G to the A. Right? G generated by G, so G has order N. By the way, cyclic groups are very important for the midterm. Okay? Very, very important. Like, write this down. It's very, very, very important. Okay? When I say very important, it means you're going to have an exercise on it. Okay? I mean, you know, be sure to know all the proofs.
Are we going to have multiple exercises on it because it's so important?
I don't know. I know there's one exercise on it at least. Okay, so please note, yes, sir. Yeah.
When it says isomorphic, it means there exists homomorphism.
Yes, exactly. Did I say that? Did I define that? We say that the two groups are isomorphic if there exists an isomorphism. Did I write this down or not? No? Okay, we say that the two groups are isomorphic. Isomorphic means, thank you, there exists an isomorphism between them. Okay, now let's prove this. Now, first of all, I have to show that the map is well defined. Phi is well defined. Okay? So suppose AN is equal to BN if and only if A minus B is divisible by N, if and only if A minus B is equal to NK for some K in Z. Now, G to the A minus B is equal to G to the Kn, G to the Nk, which is just G to the N to the power K. Now G is cyclic of order N, so G to the N is Eg to the power K, which is Eg. So G to the A is equal to G to the B. So phi of G, so phi of A, well then, is equal to phi of B. Now you have to show it's injective and surjective. Okay, you have to show it's injective and surjective. Now really here it's, you could do it, you could show it's injective and you could show it's surjective, that's okay. But let's do it in another way. Phi is clearly surjective, right? Because any element in Z, any element here, any power of G, you can find an A. So let y phi is surjective. Let y be in G. There exists, since G is cyclic, there exists, let's say, M between 0 and n minus 1, such that y is equal to G to the n, and hence y is equal to phi of the equivalence class of M. Now these two sets have the same number of elements, right? This has n elements, and this has n elements. So if it's surjective, then it must be injective. Okay? Think about it. If a function, if you have a set with n elements and a set with n elements, if the function is surjective, then it must be injective. And if the function is injective, it must be surjective. Okay, if the two sets have the same size, the same finite size, then surjectivity will imply injectivity. Which is finite. Phi is injective. Okay, so phi is an isomorphism. Phi is injective. Phi is surjective. Oh man, I didn't prove phi is a homomorphism, but that's obvious, right? This is obvious. From the most important property, what's phi of A plus B mod n? This is just G A plus B is G to the A, G to the B, which is phi of A. So phi is surject, so phi is an isomorphism. Okay? Great. Now I'll prove something called the Chinese remainder theorem. You will see it again and again, but we'll prove this. Chinese remainder theorem. Let M and N be an N. Then Z modulo MNZ is isomorphic to Z mod MZ times Z mod MZ if and only if GCD of Mn is 1. Okay? I mean, technically you have to prove this in your homework. I think I did something like that. I hear something like that. But the idea is that to use the previous theorem. Now, Z mod MNZ is cyclic, right? This one is cyclic here. Agreed? This is cyclic. It's Z modulo something. Agreed or not? Z modulo something is always cyclic gianted by 1. Now this one, I don't know whether it's cyclic. Zm cross Zn. Say m is 2 and n is 2. It's not cyclic, right? Because you have no elements of order 4. Well, the idea is to prove that Zm cross Zn is cyclic if and only if the GCD of Mn is 1. Now notice first, suppose that GCD Mn is strictly bigger than 1. Then the LCM of Mn, which is equal to Mn divided by the GCD of Mn, is strictly less than m times n. Agree? Now, if you take any element in Zm cross Zn, and you multiply by a common multiple of m and n, it will get annihilated to 0, right? 2 and 4, multiply everything, so Z2 cross Z4, multiply everything by 4, everything goes away to 0. Multiply Z2 and Z3, multiply everything by 6. I mean, 2 and 3 are co-prime, but 2 and 3 multiply everything by 6, everything gets sent to 0, right? So here, let's say take Z4 cross Z6, multiply everything by 12. 12a times 12b, you get 0, 0. 0 mod 4, 0 mod 6. Here's the same thing. LCM Mn times AB will just be equal to 0 Mn, 0 mod m. Okay? So every element will have order at most LCM Mn here. So in Z4 cross Z6, every element will have order at most 12. Take any element in Z4 and multiply it by 12, what do you get? 0, because 12 times 12, because 4 divides 12, right? A plus A plus A plus A plus A 12 times, mod 4, whatever your A is, will get cancelled. A plus A plus A plus A, B plus B plus B plus B 12 times, mod 6 will get cancelled. Okay? So, if LCM Mn is strictly less than Mn, then this group has no element of order Mn. what could go worse? The camera is off, there's no chalk. Okay, so if it's not cyclic, it's not isomorphic to Z mod M and Z. Okay? Now, if it's cyclic, I think that's a question in your homework. Well, if Mn are co-prime, if, on the other hand, GCD Mn is 1, then you can check that 1M, 1N has order Mn. This is a homework question. And hence, now if you have a group of order Mn and you have an element of order Mn, then that group must be cyclic. It's cyclic. Now, any two cyclic groups of the same order are isomorphic. So Zm. And you can explicitly write down isomorphism, but let's use the theorem. Okay, great. Yes, sir.
What is that notation with this homework at the top? What is that?
Isomorphic.
Okay.
Yeah. Okay. Great. Now let's do the first isomorphism theorem. Or you know what? Let's define something else. Pardon me?
Sorry, I have a question.
Yep.
Okay. For the end, how does I understand that everything up into the fact that it shows that it has no element order n.
You agree that every order has at most, every element has order at most LCM Mn.
Oh, okay.
Okay, and LCM Mn is strictly less than M. Okay? If the GCD is bigger than 1.
Yeah.
Is that clear? Yeah? So 4 and 6, every element has order at most 12. 4 and 4, every element has order at most 4. Take 4 and 6 and multiply everything by 12. Add everything to itself 12 times. Will go away. Yes? LCM, what do you mean? Oh, this is just a number. We're just, okay. Just so that you don't confuse parentheses. Okay? It's not easy, but you'll get used to it. Okay? Now, okay, so maybe let me take a minute of, so I will put a homework that is due on the week of the midterm, but it's not mandatory. If you do it, it's bonus. Okay? If you do it, it's bonus. Yes? Regular homework. It's a regular homework. Okay?
So next week homework is not bonus homework.
Next homework is a bonus homework. Now I tell you 2 questions that are going to be graded. I tell you like 2 of them are going to be graded. So, yeah, so to encourage you to do that. Okay. Oh, by the way, for the midterm, the dual study during the break, again, there is nothing outside the notes. On the midterm, everything is from the notes, the homework, and tutorials. Okay? So, please, please, okay?
I didn't just have time to review them because of all the homeworks and the midterm that
Yeah, yes. Guys, someone is asking a question, yeah.
When you say not groups, we got easier
So what I will do, I mean, tomorrow I'll tell you like the most important things in a lecture. In every lecture. I think I prepared it. I don't think I did it, but I will try to prepare that. The most important thing in every lecture. In every chapter, what are the most important things? This is definitely not an exhaustive list, right? I can always examine you on things that I might not have mentioned. But these are the key items, if you want, the key items, if you want, or the key theorems in every single lecture. Now, what you have to do is go down. Don't usually some people study. They read, yeah, I know how to do that. Yeah, I know how to do that. Then the exam comes. You just read it like for 2 times, and you read it quickly, so you won't remember it. So what I would do is like sit again and rewrite it. Rewrite it. It will take you 3-4 minutes by proof. but that's okay, right? It's not a big deal. Okay, so 3-4 minutes. You say you have 100 proofs. So 300 minutes. How much is that? Let's take another
5
round.
hours.
Let's take 600 minutes. How much is that?
Oh my god, that's 10
10
hours.
hours. Okay. 10 hours for studying for a midterm. That's fair. There's no practice. The practice is in the, everything is from the notes. And the homework, yeah, I said everything is from the notes.
But we shouldn't rewrite ones that we already know from previous classes. Though.
Pardon me?
We don't have to rewrite ones we already know
Guys,
from previous
please, somebody's asking a question. What do you mean?
We only rewrite new ones that we didn't know before, right? We don't rewrite ones we already knew.
No. Like everything is from this class, from 235. Nothing from before. I'm not asking, all the questions will be familiar. I mean, even the numbers, there are like some numerical examples. Even the numbers are the same. I said, the first question is a Euclidean algorithm. Okay, I picked two-digit numbers. Okay, the two numbers are 2-digit.
So we just have to.
And those are examples from the notes or from the homework. I think we've done 3 of them, right? 3 or 4 of them. So like you can know which ones are there. Okay, so everything is from notes, homework, or tutorial. Now, if you did not study the notes, good luck. Okay, it's but again, and by the way, there is one thing. So yesterday I put, on the last homework, I put a question that I did in class. Just to see like how many of you will look at the notes. So I put the question is that if G is cyclic, generated by G, then G is generated by G to the k for any k that is relatively prime to the order of G.
Yeah.
Right? Now this was exactly done in the class. I exactly have done that. Now I've looked at the answers. Yeah. And the proof is just one line, 1 or 2 lines. And the answer seems, I mean, there are good answers, but it seemed to be not connected to what you have done in class. I mean, it is connected, but like the class allows you to answer it in 2 lines, and I've seen very long answers. So please, before you go ask for help, do look at your notes, okay? Yes? Yes, you're allowed to state it unless I'm asking you to, yeah, exactly, yeah. Yeah.
Just to clarify, the right proof is you basically saying like a b to the power of LCM of n is since it's less than
Mn.
So, yeah, since it's less than mn, it doesn't have
An element of order Mn, so it's not cyclic. Very good. Yeah. You had a question? Someone here had a question? Yeah.
So from which tutorials are the questions selected? Because I don't think that the questions that the tutorial
Are they will be identical, okay? All the questions are going to be done in the 3 tutorials. Lucas.
What if I basically just like state a theorem that I saw in the book? Would that like
Sure. Sure, you could state that, but if it's not something we have seen in class, you should prove it. Okay?
Okay.
Yeah.
Can we say we proved something from a homework even though we don't know which
Yeah.
homework it's from? Because
Yeah,
we
yeah,
just
so
kind of proved it already. Right?
no, if the question asks you prove this theorem, you
No,
cannot say
no,
use
no.
homework 5, right? See?
Yeah, no.
Right?
No, I mean we proved it, but using what we
Yes,
already knew by
yeah.
that point.
So I was usually I was careful when I was writing that thing. I was telling you, you may use without proof this result. Okay. For example, one question could be, I don't know, state Lagrange's theorem. Okay. And then the next question could be prove Fermat's little theorem. Okay. Now for Fermat's little theorem, you need Lagrange's theorem, right? You can use Lagrange's theorem without proving it. Okay. Great. Okay, so I mean, nice 10-minute chat. And then, okay, see you all tomorrow. Tomorrow,